Here we take a look at the halohydrin reaction. This reaction is a variation on the halogenation reaction of alkenes, and the variation occurs in that in addition to bromine reacting, we also have water present. So we know, and we've seen previously, that if we add only bromine to an alkene, that we end up with an anti-addition of bromines on the two carbons of the alkene. But when we also include water, the addition is still anti, but one of the carbons ends up with a hydroxyl group instead of the bromine. So perhaps not surprisingly, the mechanism of this reaction does share some of the properties with the halogenation mechanism. Specifically, in the first step, the alkene attacks bromine, which breaks the bromine-bromine bond, and simultaneously the bromine attacks back to the alkene. This is what forms our three-membered bromonium ion. This here, though, is the difference. And the difference is instead of bromide opening up this three-membered ring, our nucleophile is now water. Water attacks and opens up the three-membered ring. Because that three-membered ring is essentially on one side of the alkene, the nucleophile that comes in has to come in from the opposite side. And so while there's no preference for whether that ring is going to form on the top or the bottom, we do find that the bromine and the alcohol will be on opposite sides. Finally, the OH group has to lose a proton to become the alcohol, and we get our product. Now, in the case of halogenation reactions, we didn't have to worry about alkenes that were not symmetric. Because if you're putting the same group on both carbons, it doesn't really matter. But if we have an alkene such as this one, a very simple alkene that's not symmetric, now it does matter. Because the two possible products that could form are not the same. They're isomers of each other. So how do we determine which one of these is favored or more likely to form? Well, we can do that by again looking at the mechanism. And we know our first step of the mechanism is formation of the three-membered ring. It's at this point that the water has to decide where it's going to attack. Does it attack at the more substituted carbon or at the less substituted carbon? And the key in this reaction is that we're dealing with something that's positively charged. And not just the fact that that bromine is positively charged, but also that the bromine is an electronegative element. So we know bromine polarizes, carbon halogen bonds. The halogen ends up with a partial negative. And it's going to do that even more so in this case because it's positively charged. So of the two carbons, we have our more substituted one here in yellow, and our less substituted one we'll highlight in green. Of those two carbons, which one is better able to support some of that positive polarization from the bromine? Well, the more substituted a carbon is, the more stable it is as a carbocation. So that yellow one, the one that I've highlighted in yellow, the more substituted carbon can bear more of the positive charge of that cation. And if it can bear more of that positive charge, then it's going to be a better electrophile. And so for that reason, the water will attack at the more substituted carbon. Now, keep in mind, and this is something we'll see later on in the course, that if this ring that was being opened was neutral, that can have a significant role on how this step goes. But the water here attacks the more substituted carbon. We get this intermediate, which then loses a hydrogen to get us to our product. So we can look at some other examples. And we can continue to look at these with bromine and water. Or we can switch over to chlorine. Doesn't really have a significant impact on the results of the reaction. In this first example, it doesn't matter which carbon we put the bromine and which one we put the alcohol on, because the molecule is symmetric. Again, the only thing that does matter is that we show that they're going to be on opposite sides. With chlorine as the product, we'll see chlorine instead of bromine. But the OH group will still be at the more substituted carbon and the chlorine at the less substituted. Same thing down here.